Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. I hope your Easter break went well, that you could relax a little bit, disconnect your brains, and now you are back for a new lecture in information retrieval. This will be a mathematics lecture. I'm not going to hide that I love math, so I enjoy doing all of that, but it's not only for the purpose of mathematics in itself, it's also something that I think is some sort of acquired taste in computer science. It is very addictive. It is learning how to squeeze performance out of computers. How do you manage to process more data with less space? How do you manage to process more data with less CPU, with less machines? And that actually saves you a lot of money. It saves you a lot of time because things are much faster. It's truly something that after a while you enjoy doing. You can't have enough of it. We kind of already did that last week with index construction, because here we try to scale things up and out. So we learned how we manage to build indices on collections that do not fit in memory. We even learned to index collections that do not even fit in a machine, like the entire web. We learned how to index it. But if you only do that, if you only scale out to multiple machines and parallelize things, that might actually quickly cost you a lot of money. There is a second step when you do these sort of things, which is compressing stuff and getting more from less hardware. And this is exactly what we are going to go to be doing now. So what have we seen so far? So a quick recap previously in information retrieval. We have looked at Boolean retrieval, which is a first naive system that takes documents and then you take a query with AND or not, and then you return a subset of the documents, unranked, no sorting at all, it's just a subset. Then we saw that we can achieve this with a structure called a standard inverted index. This is the basic of the basics, right? That has the terms on the left. Then you have the document frequencies in purple, which are the counts, and then you have the postings list. And every one of these postings, so the blue rectangles, corresponds to one use of a term in a document, right? I think in object-oriented programming, it's commonly called a use posting. All right, so this is the standard inverted index. We saw that when you query the actual terms, you actually need a data structure in order to facilitate and accelerate the lookup of the terms. And you can do this with hash tables or with B+3. So you see what you learned in algorithms and data structures that's actually directly useful in database lectures. So it's either or, but you just need to know that with hash tables, you do not support ranges. If you want ranges, then you really need the B+3s. And then we started introducing additional features into the system. We support wildcards. We saw how to do that. We support spell correction. We support phrase search when you want words that follow each other. And for this, we actually extended the standard inverted index into less standard indices. That's basically, this is an example with bywords indices, where instead of terms, we have pairs of terms, but it generalizes to any number. We also looked at the positional index, which still have one term at a time on the left. But if you look closer at the postings, now we have the detailed positions at which the terms appear in the original documents. So it's no longer a set of word semantics. Now it's a list of word semantics, because we do care about the order. And these two extensions, there are two different extensions, they both allow you to support phrase search, right? In different ways and with their advantages and drawbacks. All right, then for spelling correction and wildcard queries, we looked at the trigram index, but it generalizes to kgram or whatever number of letters. And that allows you to quickly retrieve the words that contain a specific sequence of characters, right? And the dollar is used for the beginning and for the end of the words. Then we saw term IDs as part of index construction. This is, it's actually called the dictionary encoding in the database world when you do this. In order to save space for terms that repeat during index construction, we replace them with IDs, term IDs, right? So that is also something we covered. And then in order to build the indices when it does not fit in memory. You might remember that we partitioned the input collection into different shards, and we process them one shard at a time. The first way to do that is called blocked sort-based indexing. The other one is called single pass in memory indexing, or SPIMI if you want to abbreviate it, and BSBI for that one. So these are very similar. I would call it the first generation and the second generation, because it's basically just an iteration and successive improvements, right? So you basically build a mini index for every partition of the input, and at the end, you merge all of these indices into a bigger index, right? Then we looked at what happened when the collection gets updated all the time with new documents coming in, with updates to the documents, with deletion of documents. What do you do if it constantly changes, which is the case of the web? If you want to index the web, you have to deal with this. So one way of dealing with this is to have a short-term index in memory that is an auxiliary index, and a long-term index that is on disk, and then you just query both, but the recent changes would only be in the index in memory, right? But then we saw that actually doesn't scale, because if you do this and you just merge regularly the auxiliary index on the disk naively, just like that, every time it's full, you merge it again, that also doesn't scale well. It's not efficient. There is a more clever way to do that is based on this game 2048. And the idea is that you double in size every time you merge, right? So this is this, you might remember this. Every time the memory is full, you merge, but then you only merge whenever you have two indexes of the same size, then you merge them into an index twice as large, right? And then you keep building larger and larger indices, but because you're using powers of 2, that's the power of powers of 2, you are actually doing something logarithmic in complexity, and that's actually very nice. And these are called log structured merge trees, LSM trees, and it is extremely popular in big data for we'll see at the master's level for H-base, big table, Cassandra, and so on. So this is the way that you can deal with this. All right, and that's what we've been doing until now. That was just a refresh. And now what we want to do is save money, save memory, save disk space, and save on the machines that we are going to use by improving the whole system, compressing stuff. Before we do this, we are going to start with some analysis, and we are going to look at two, I would call them empiric theorems. It's not really theorems, it's more like empiric remarks on the behavior on the systems on large scales, of not the systems, but the collections of text, basically. So we are going to look into two laws. The first one is called Heaps law, and the other one is called Zipf's law. So imagine that you are indexing collections, and you start maybe with 10% of the collection, and in this 10% of the collection, you're going to do all of these things we've looked at. You know, you tokenize, you process, you lemmatize, and so on and so on. You use the Porter stemmer and so on, and then you're going to come up with terms that are on the left side of your index, right? And so the first question that we are asking ourselves here is, if my collection grows, I add more web pages, I add more books in my collection, how does the number of terms grow? That's the first question. So I'm going to use letters a lot because, again, I said it's math, so now I need variables for them. So just so you know, and you get used to it, it's the same conventions as in the book that we're using, actually. When we use uppercase N, we mean the number of documents, the number of books, the number of web pages, right? Number of documents. T is the number of tokens, but here we mean the positional postings, right? It means that it's not just a specific term or a specific occurrence of a term in a document, it's a specific position in a document. That's a positional posting, right? And then M is the number of terms that they are, which you could also call the the actual terms. And a non-positional posting would be a pair term document. For whom is that clear? We've already seen that. Okay, so N is the number of documents, T is the number of tokens, the number of words that you see in the book, and in total, and M is the number of terms. So M is the height of your standard inverted index, so to say. Okay, Now that we have said that, this is the question. The number of terms, is it linear? Is it polynomial? Is it exponential? Is it hyperbolic? In a good way or a bad way, could be hyperbolic this way, we have a problem, could be hyperbolic horizontally. What do you think? Any ideas? Yes? Maybe we can... Is it working? Yes.
I think it's the lowest curve.
The lowest curve, so you would bet on the hyperbolic one, right?
Under the assumption that there's like a constant amount of total terms.
Yeah, so that's very good thinking. So this would basically be based on the fact that a language has a limited number of words in the dictionary.
Yes.
Right? Okay, so this is where your bet goes. Okay, do we have any other bets? Who agrees with this? Makes sense, right? Who has a different opinion? Nobody with a different opinion? On Zoom, does anybody have a different opinion on Zoom? None? We love critical thinking at ETH, so it's fine to have different opinions. Okay, so I'm going to tell you then that your reasoning makes perfect sense. This makes perfect sense. In fact, this is what I would have expected. Oh, somebody on Zoom reacted?
Yes, new words appear in languages sometimes.
Ah, so we have somebody who disagrees. So you disagree with this. So what do you think? What kind of curve would that be?
So
Oh, cannot speak, but you can write in the chat if you want. You can share. So let me simplify for you. If you would you say linear? Would you say it's in between linear or hyperbolic? Would you say, what would you say? Or above linear?
Below linear.
Below linear. So we have a second bet, below linear. Let's do a poll now. Let's see in the lecture hall. Who in the lecture hall would vote for the hyperbolic one, the horizontal asymptote? Raise your hand if you would. And on Zoom too, you can raise your hand. Horizontal asymptote. Do we have many votes on Zoom for this? Okay. Let's vote again then on the sublinear, but without the horizontal asymptote. Who in the lecture hall would bet on that one? We do have one courageous person over there who would bet on above the horizontal line. What about Zoom?
I don't know if it is for this one or the previous one.
Oh, okay, yeah, that's annoying. Okay, but we seem to have a Zoom versus lecture hall thing here, right? Okay, so of course, if we want to analyze data and so on, we have linear regression when we love when things are actually linear. Well, it's not linear, that's for sure. It's not going to scale linearly in terms. But if you look at the log-log scale, so you plot the log of terms and the log of the number of tokens, so log of M and log of T, and if you try to actually do a linear regression with that, you're actually going to succeed. So you're actually going to find, so if it's linear in log-log, then it means that you have an equation like exponential of A times T to the exponential of B. So of course here it's above linear, but you can have negative exponents too, right? Or smaller than 1 at least. It turns out that this works if the exponent is 1/2. And in fact, this is growing in the square root of the number of terms. So it means that you actually won, and on Zoom also you won. This is totally unexpected. That's a surprise for me because I would exactly have the same idea as you suggested, right? The number of terms is limited. The number of words that you can have has an upper limit. But in practice, somehow it seems that it keeps going up and up and up. And this is along the lines of what you said on Zoom, that the number of words, you keep creating new words, but it's also that when you index the web or very large collection of documents, you also have a lot of wild stuff happening, right? A lot of new words happening, but also maybe because of you might have a lot of books in the collection that are highly specialized in something. So you might have tokens that are not actually words, like phone numbers, emails, and so on and so on. So I think this is kind of the intuition why it doesn't have this horizontal asymptote, right? But that was a very good guess, and this is why we had actually a minority of people thinking that it would not have the horizontal asymptote, right? Okay, so this is a surprise, and that's the first surprise we have, and this is in fact called, I put it here, Heaps law. This is Heaps law that tells you that the number of terms, so the height of your index grows in the square root of the number of tokens in your collection. You could say the same thing, by the way, if you assume that the books have some average size in number of pages or number of tokens. It doesn't really matter if you plot the terms against the tokens, T, or the terms against the number of documents, N, right? If you assume that the number of tokens in a document is on average pretty much the same, then you'd still get this square root effect, no matter what, right? Okay. So this is our first surprise, right? And the insight of the day, Heaps law says that's the square root of everything. Okay. So now we're going to move on to the second law, that is Zipf's law, and then we're going to vote again and see your ideas again. What if now we look at the frequencies of the terms, the frequency at which they will appear as positional postings in the document? Now, I love learning languages, as you noticed a few weeks ago, and in particular, when I try to learn a language, what I love to do is I look up a frequency sorted table of terms. I look for the 1,000 most frequent words in this or that language. Because if you focus on these words, you very quickly have a high density of coverage of understanding of a language if you optimize in that way. And so you can actually do that. For example, you can take Wikipedia and try to analyze the words in that way. So the, of course, that's a stop word, right? It's all over the place. Where is quite common, nearer, moderate, champion, less common, stocks, parallelogram, pachyderm, hope it's pronounced that way. It's also the least frequent words. You don't know how to pronounce them in English. That's another problem. Capacitance, that's something with electronics, and germanium, now almost chemistry, maybe also has to do with electronics too. So basically, these are the frequencies. And it kind of feels logical, right? That there's very common words and there's less common words. But now the question that I ask is, if we rank all of these words, I actually did that. I took a Wikipedia data set and I run, I think I used Spark or something to do that. And I ordered them by decreasing frequency. And I plotted the frequency of each term by decreasing frequency. And this is what I got. What do you think that is? You can almost guess actually on that one. What kind of curve do you think that is? Anybody? Yes? Maybe we can meet. Thanks a lot.
I would guess it's x high -1.
Minus to the power of -1? Yeah, exactly. 1 over x, right? That's exactly what it looks like. And in fact, that's correct. And the way we see that is, again, the log-log scale. If you look at it in the log-log scale, you actually see a line. So this is why you see, okay, you can do a linear regression with that. And so it's, again, going to be an equation like that. So it's typically the same thing, actually, as we already had with Heaps law. But of course, now the exponent is not going to be 1/2, it's going to be -1, as you said. And this is true, -1 it is here, which means that the frequency is basically some constant that I called k, we can call it whatever we want, divided by the rank. It's 1 over x, right? So that's it. That's a 1 over x curve. Of course, if you go very, 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 very far, because I did it with the whole of Wikipedia here, that almost feels like a vertical line and a horizontal line, right? So yeah, but it's 1 over x. This is called Zipf's law, right? That's a lot of consonants in a row, P, F, S, L. But I think in German, we are kind of used to having many consonants in a row. All right, so Heaps law, the number of terms is in the square root of the number of documents or the number of tokens. And Zipf's law tells us that the frequency of the terms is in 1/x. Okay? That actually is a big surprise to me. Do you know why it's a big surprise to me? It's actually scary. Who is surprised by this? You are surprised. Why are you surprised? Let me try. Oh, almost. Thank you.
Thank you. I wasn't quite sure. I thought that it would be 1 divided by something exponential, actually.
Exponential. Why would you think that? It's a very good point. Why would you think that?
I don't know, just intuition, I guess.
Intuition, yeah, that's a good intuition. On Zoom, does anybody want to express surprise about the 1/x? If not, I'm going to guide you to why I am surprised. Okay, let me guide you. When you have something like that, you want to renormalize. Can I renormalize that thing? Of course, it's finite, right? But imagine it goes to infinity, because we saw the number of terms goes to infinity. It's the square root, right? So it goes to infinity. How do I renormalize this thing? Do we have any mathematicians here? Yeah, you can throw it back if you want, or you can speak also if you want to say.
Well, I don't know if that's what you mean, but the sum doesn't converge.
Exactly, that's exactly it. You might have heard, or you might have tried to sum 1 + 1/2 + 1/3 + 1/4 + 1/5 and so on all the way. That doesn't converge, doesn't sum, it goes to infinity. And if you want to renormalize, you would divide by the sum, right, to infinity. But the problem is that if that sum actually doesn't converge, there is no way you can renormalize that. Doesn't work. And that's very surprising to me, because I would have thought, there's some kind of distribution that you can renormalize to 1 as a probability distribution. That would have been natural. But somehow the real world is full of surprises. And here we are with a 1/x that we cannot even normalize. Well, we can normalize it if it's finite. And in practice, you're going to have a finite collection. So we will renormalize in this way. But you cannot renormalize all the way to infinity. That's the real life of human languages somehow. All right, so these were the 2 surprises, that square root and 1/x, and this is Heaps' law and Zipf's law. Okay, so now that we have had these insights, we can move on to how we apply these insights to the compression of our index. But first, I would like to show you what we already did without maybe being aware of it, but we already did compression in former lectures. For example, we mentioned removing numbers. We mentioned grouping similar words in equivalence classes, which is also a way of reducing the number of terms. For example, case folding. We remove stop words, which is also an excellent way of getting rid of plenty of tokens. We used stemming and so on. All of that is going to reduce the height of the index, M. That's going to reduce the size of M. So this is great. Is it doing a great job? Yes, actually, we can measure that. So this is what we've done before. So we can measure it in the 3 ways, right? We can look at the impact on 3 things. First, we can look at the impact on the number of terms, M. Again, that's the height of my index, the number of posting lists that I have. And you see that removing number doesn't help, but case folding and stemming actually helps, because that's directly working on the terms. But then instead of the terms, we could look at the non-positional postings. These are my blue rectangles in the index. It's the use of a word, of a term in a document. Here you see that stop words are actually incredibly efficient at that. It's logical, right? Because as soon as you remove D or Is or A, then you're going to remove plenty of these blue rectangles, right? Because you're removing the posting lists that are the longest, right? So this works well. Less so on stemming, case folding, removing numbers. Why? Because if you stem or case fold, you're just unioning the list, right? So that might not help much. And finally, you can look at the number of positional postings, meaning that every single occurrence, list of word semantics, every single occurrence in the document If you remove the stop word, it's a minus 47%. It means that basically half of the words in text are actually stop words. Okay, that's surprisingly high actually, but seems to be what they got here. And so if you apply all of this together, you see cumulatively minus 33%, minus 42%, minus 52%, right? So that means that on the height of the index, I can remove 1/3. On the blue rectangle, so the postings, I can remove 42%, and 52%, we don't actually store that in the index, except in the positional index, then we would get minus 52%. Yes? Oh, because they do not accumulate straightforwardly, because you might have redundancies. That if you solve and if you compress with the one, then the compression effect of the other would be less than if it was alone, right? It's kind of it's a removal of intersection between them, right? But that's a good question. You could have thought, okay, that's it compresses in that way. That's one reason. The other reason has to do with the fact that it's not an addition but a multiplication. With the fact that, you know that removing 9% means you multiply with 0.91, right? And then removing 47 means you multiply with 0.53. And so if you multiply this, it will not sum up. It will only sum up asymptotically. If the numbers are very small, then they would sum, but if they are larger, they would not, right? It's like saying that if you have 10% of interest on an account, it's plus 10%, the second year plus 10%, but the cumulative effect is not 20, it's 21. That would be the same, because 10 times, no, did I get that right? No, I cannot even do math properly anymore when I do it live. No, it is 1.1 times 1.1 is 1.21. So 10% and 10% is 21%, doesn't that either? Did I answer your question? Yep. All right, so I suspect there are these two effects that basically give us these non-summing things. Okay, so that's already good, right? That's already excellent news, and this is something we already have from the previous lectures. But can we do better? The answer is yes, we can further improve and get something better. So let's start with the left part of the standard inverted index. I'm going to remove that thing at the bottom. It's only in the lecture hall that we see it, but it's blocking the way. Oh, of course, it appears again. There you go. So let's start with what's called the dictionary. It's the terms on the left, and let's ignore the postings for now. So you remember that we store them in a B+3 if we want to support ranges. So we have pointers to the postings list from every one of the leaves in there, and the leaves are actually the terms that we have in our index. So I told you that we have on disk all of that at the bottom, and we load into memory the upper parts of the B+3, which is small enough. Okay, so technically, we could make it fit in RAM, just the part that is at the top, and the postings would be on disk, right? But if we don't compress anything, it might not fit in RAM. Maybe the actual terms might all be on disk. Can we do something about it? Well, let's try to run some computations. Let's try to calculate how much space it's going to take. I'm not looking at the postings at all, just the dictionary part. So every single term might take 20 bytes. Let's assume we cap at 20 bytes, 20 characters. Then I have my document frequency, takes 4 bytes. And then I have 4 bytes for the pointer to the postings list, right? Or for where it is. Well, we have a first problem with that, is that if we have long words like supercalifragilisticexpialidocious, then that doesn't fit. That's the first limitation. But let's still assume that 24 and 4. We can do better than that with another approach 2, which consists in the concatenation of all terms, all of them. So we no longer have these constant reserved 20-byte blocks in memory, which would be a waste of space with unused characters. We just concatenate all of the terms in a huge string in memory, and we have these pointers, these additional pointers that tell us exactly where it starts and where it ends, right? So that would be a bit of an optimization. But of course, we still need some extra space for this string as well, which I didn't count there. Here I didn't count the actual terms yet. And it turns out that this more or less takes an average of 8 characters if you average the length of the terms, right? So 20 here is not an average. It's a cap. It's a hard cap in the length. Here is an average. So on average, you're going to have 8 bytes per word. Some will have less, some will have more, but the average is 8. Then there is a further optimization that consists in only having this pointer from the rows of our inverted index only every k terms. So we have k less of these pointers in there. However, we need an extra byte in order to encode the length of the terms. Do you understand why here we don't need it, because we have a pointer at the start of every word, which is also the end of the previous one. But if we only have a pointer every k words, then we need to know when they end. So here I need to say there's 8 letters here, 3 letters for CPU, 4 for data. So we add 1 more byte in here, right? So you see, if you add stuff, right? Here you have 28. Here you have 4 plus 4, 8, 11 plus we are at 19. That's already better. And now we have 4 plus 4 plus time 3 over k plus 9. If you pick k large enough, then this is going to help, right? So you see that we're making progress here in the space that actually takes. Who agrees with that? That's intuitive, right? But of course, if we start doing that kind of things, there is no free lunch. We save space, yes, we save space. But you know that in computer science, whenever we save space, we're going to pay it with time, right? And vice versa, right? There is this general rule. And this is exactly what's happening in here. It's a compromise, because if we have built something like this, we are putting that on the CPU to decode that stuff, because now it's no longer straightforward to decode. It's extra computing, right, that we need. So if we really have a problem of space and we are ready to pay in terms of CPU usage and put more load on the CPU, then we can go ahead and do that, right? It's always a compromise between space and time. Now another thing to consider in the index, because if it's a B plus tree, it has a tree structure like that. In terms of performance, if you want to analyze what that does to the CPU, you need to do some complexity analysis on how many comparisons are we going to need in order to go all the way down. So if you have a perfectly balanced tree like this, then for example, here you have 1 extra memory seek, here you have 2 extra memory seeks, that would be a B tree, not a B plus tree here. And then on average, for this, if it were a B tree, you have the average of all of that is 1.4. But imagine that your tree is more like that, right? Why would we have a tree more like that? Well, this is the case where we have this here. We have only every k terms, right? So now we have a tree, but we group the terms in groups of k, right? If we do that, then we get a structure more like this in terms of comparisons, right? So now, if we average on that, that's an example of 2 extra memory seeks. Now we have an average that is worse. So we lost a little bit in performance. It's only an intuitive way of looking at it, right? Okay. So we save on space with that kind of tricks. We pay in terms of more time and more load on the CPU. It's a price we are ready to pay. There is another approach, though, that can also gain some space. Do you see what's happening in here? What happened here? We notice that there is a lot of redundancy. If you have a very large collection of terms in a dictionary, it gets repetitive if they are sorted alphabetically. Automata, automate, automatic, automation, and they are sorted alphabetically, right, in the index. So we can compress by sharing prefixes. Now I can put this little star in there, automate, automate, automatic, automation, and then I save some space again, right? So I'm going to have less bytes. Who agree this saves space? Okay. However, again, you pay it in terms of performance because you're going to have extra load on the CPU to rebuild the original terms, but you can save space. So you see there's a lot we can squeeze. So now that we have considered this, all of these ways of looking at things, we can start looking at how much space we've actually saved. And I picked that from the book where they actually did the math. So I trust them on that. But maybe if you have time, you can also experiment yourself and see if you get similar results. So we have a collection of 960 megabytes in here. And if we use a fixed width encoding, that's the first approach where I cap at 20 bytes, but I waste the space if the word is shorter than that. Then the size of the dictionary, so that's what's on the left of the standard inverted index, is 11.2 megabytes. Then if I use my unique strings and pointers, so I have a huge string where I concatenate all of my terms, then that goes down to 7.6 megabytes. Not bad, right? Then we use the blocking, meaning that we do it only every k terms, right? We group the terms by k equals 4 in that case, so 4 by 4. We go down to 7.1. It's a small gain, not enormous, but still we squeezed a little bit more in it. And if we use the blocking and front coding, meaning that we recognize it's alphabetically sorted and we have prefixes in common, then we go down to 5.9. So you see, we almost squeezed 50% in here. If we apply all of this, we are almost at half of the space that it takes. So we managed to squeeze in half the size of our dictionary, right? So that's excellent news. If you accept to pay the price with more load on the CPU in order to decode all of these things. Okay, we have a few minutes left. So this is it for the dictionary compression. So now we're going to move on to the compression of the postings on the right. Okay. So let's look now closer at the postings. What are they? Well, we saw that on the logical level, a posting is a pair with a term in a document. It's the appearance of a term in a document, right? Where we don't look at the repetitions and so on. It's a standard index. However, we don't actually store the pair every time because the term is the same for all of them in the same row, right? They have the term in common that is on the left. So this is why we only share the document. We only store the document and more precisely the document ID. What is the document ID? It's an integer. Should be no surprise because this is what we've had until now. So if the posting list is a list of integers, then mathematically the problem we have is how do we compress lists of integers? How do we do that? How do we squeeze lists of integers into as few bits as possible? And now that starts smelling like information theory, right? Who is a bit familiar with information theory? Right, so there's going to be some of it in there, right? So there's the notion of entropy, there's the notion of, how many bytes or bits do you need at least to store this? So we're going to try to squeeze that as much as possible, compressing lists of integers. As always, we're going to start with naive approaches, right? So the very naive approach would be to not even try to compress anything at all and just say, okay, we're going to take a constant number of bytes, let's say 4 bytes. What does 4 bytes give me? Well, it gives me document IDs all the way to 4 billion, right? That's 4 bytes is 32 bits, so 2 to the power of 32, it's 4 billion, right? By the way, you know how to quickly calculate power of 2 approximation, right? Because 2 to the power of 10 is roughly 10 to the power of 3. So if you have 2 to the power of 32, 2 to the power of 30 is roughly a billion, right? And then the 2 to the power of 2 gives you 4. So 2 to the power of 32 is 4 billion, right? Just a quick way of approximating powers of 2. All right, so now we can support up to 4 billion documents. If it's not enough and you have the entire internet and it's more than that, you can just go for 8 bytes, 64 bits, if that's better. But let's take the example of 4 bytes. Right, I even have the exact number there of documents. So that sounds like something you could do, right? And I think if that was even what was done in the exercises until now, right? But that actually takes a lot of space. You have 4 bytes every time. Can we do with less space? Of course, the answer is yes, because otherwise I wouldn't be speaking about that in front of you. So yes, we actually can. And in order to do that, we are going to start with some insights. These postings lists, lists of document IDs, are there just lists of any integers, any lists of integers, or is there some assumption in there on how they look like? Like, can I give you any list of integers and that's going to be a postings list? Yes, over there. Where? Oh, the microphone is. Maybe you can try directly. Wow, you're good at this, better than I am.
For a lot of words, there's not going to be two numbers directly in a row, so you probably wouldn't have 1056 and 1057, but you might still have them in close proximity because you're talking about the same topic, so you'll reuse the same words.
Yes, so there is this notion of proximity that will actually help us. So this is a very good point. There is another point that will also help us here. It's kind of related to what you are saying. Is there any constraints on these integers? Yes? It needs to be sorted exactly. That needs to be sorted. So that is actually information. It is always sorted. Yes, and somebody agrees with you also on Zoom. So yes, indeed, it is not just a list of integers. It is a sorted list of integers. Can we use that to compress? Of course we can, because now that we know it is sorted, I'm going to shock you, we are going to take the first derivative. It's kind of an abstract way of saying that. For a sequence, we are just going to look at the deltas, the gaps. So we are not going to actually store the actual document IDs. We are going to store the gaps between the document IDs. So the first one, we have no choice. So the first one, we'll encode it as it is, the first document ID. But all the subsequent postings, we're only going to store the gaps. And now the gaps can be any integers. Do you agree with that? The gaps can be any integers, right? Okay. Who understands that when I say that's the derivative? Right, it's f prime, kind of a sequence. It's the deltas. Okay. And of course, since it's a growing sequence, you know that the derivative of a growing function is actually positive, right? So this is why we still have these positive integers in there. Okay, so we will encode the gaps, which means, and this is something mathematicians love to do, we have just brought ourselves back to some known problem, which is encoding integers that don't need to be sorted, right? And then now we have plenty of literature to do these sort of things. But just doing that is going to help us save some space, right? And the key here is that the gaps might actually not be that big on average, right? For most of the terms, they appear in a reasonable number of documents. And so the gaps are going to be small enough. So the space it's going to take to store these gaps should be less, right? Okay, so this is what we get out of this. So here, that's the encoding of the actual, the zeros and ones that you see here. These are the actual document IDs, right? But now we encode the gaps, so +2, +5, +1, +3. It's all positive because that's sorted. And now I'm encoding the first document ID here, but then I'm only encoding the actual gaps. So this is 2, this is 5 in base 2, this is 1, this is 3, and so on and so on and so on. And maybe I can use less bits for that. So in that case, I use only 4 bits for the gaps. Okay. Does anybody see any problem here? Yes? Maybe you can throw it back over there.
So how do we know how much space we have to allocate, or the size for the number where we store the gap in, because it can be arbitrarily large?
Yes, yeah, that's exactly it. Here I took 4 bits. That's because I actually had a frequent term in here. Maybe that was the or is or where, right? But what if I have here instead germanium, for example? Then the gaps are going to be larger. So if we use a naive technique like that with a constant size, then we have to consider that there are terms that are not frequent. And then we have to, maybe we need 4 bytes again here. But that means we're back to square one, because now we again have a sequence of blocks of 4 bytes, as many as terms. So we actually did not gain anything by doing that. So that's the cliffhanger that I leave to you for the break. And in 15 minutes, I'm going to show to you how actually we have a way of circumventing that problem for doing something better. All right, so I'll see you in 15 minutes where we will be doing that. Thank you.